how to describe shapes of data. So what do I mean by that? Right. Imagine you collect a lot of data and you made what's called a histogram. Now, histogram is something that basically looks very like a bar chart, but the main difference is that there are no gaps and that the data. So imagine I collected data and this was 16-year-olds, 17-year-olds, 18-year-olds, 19, 20, 21, 22, and then away over here, there was me, right? Let's just pretend that was the kind of data that we've got. That's called a histogram, right? It's basically a visualization of that data. The horizontal axis would be the age of the student, if that's where this data came from. And the vertical one is always the frequency. So since histograms, almost all data can be made into a histogram, it's not surprising then that they create, actually, let me put in a couple more. There's 28, there's 29, right? They put in a lot more time into describing what's going on. So I'm going to give you a whole load of jargon names. First thing I'm going to talk about is this shape has basically got one hill. Would you agree if you thought of it like a hill? It's a single hill, right? And if you have a histogram that only has one hill, you call it unimodal. Now, it is possible, and I'm not going to draw the rectangles because they take too long. Can you imagine a histogram? I know that doesn't look like histograms, but can you imagine a histogram where there was two distinct hills, right? That could happen, right? And if your data looks like this, we use the bimodal. So we would say, I collected some data and the data was bimodal. You would say, oh, so it's got two distinct hills, right? It climbs up and then it drifts away, but then it climbs up again and drifts away, right? Bimodal. Now, you could say, well, what do you do with 3 hills and 4 hills and 27 hills, right? Do you start going through various names? Well, you could, but we don't. For instance, if it had 3 hills, we could call it trimodal, right? And if it's 4 hills, we could call it quad modal, but we don't. After 2, so it doesn't matter if it's 2 or 22, but if you have a whole load of data and there's more than 2, we just call it multimodal. So there's your first term. If you look at a histogram then, and it's got a noticeable hill to it, and there's only one, you'll say that that data is unimodal. If it's got 2 obviously distinct hills, it's bimodal. If it's got, like, in this case, what that'd be 3 hills, right? Or 4 or whatever, you call it multimodal. Now, sometimes you get data that I describe as looking like the skyline of New York. You know, like that. Can you imagine data where every rectangle is kind of like the next one, right? It's not exactly the same height, but aren't they all very close to each other, right? If you see data that looks like that, that clearly doesn't have any hill, but they are all roughly, very roughly, you're allowed to be very roughly, right? We call that shape uniform. So if I wanted to describe the shape of my data and it ended up being a whole load of things almost all the same height, I would say my data is uniform. You know, uniform in the, I'm pretty sure uniform, do you know when people wear uniforms, they all look the same? I'm pretty sure that word has a Greek or a Latin root that means the same, right? So the word uni, right, form, all the same.
Is there a term for when they are they're actually all the same? Like,
no, they just call them uniform if they are perfect match. And sometimes you have to make a judgment call. What do I mean by that? Can you imagine that you might have some data and you might say, that looks to me like a bit of a hill. And that there looks like another bit of a hill, right? Maybe to you it does, maybe to somebody else it doesn't, right? Now, what the judgment call I'm talking about here is that you might have to say, well, in this case here, couldn't I say it was bimodal? Or you might just say, nah, they're not really that different. I would go with uniform. If I had to, I have to pick something, I would pick that. If I've only given two choices, you would sometimes make a judgment call. Thankfully, any question you get is going to be obviously something, right? So you won't have that gray area where is it uniform, is it not? It'll be clearly uniform, or it will be clearly unimodal or clearly bimodal, right? So we won't do that to you because it's kind of unfair. Now, another feature, back to my original set of data. Sometimes, not always, sometimes you get almost all your data and then you get a noticeable gap. Actually, if I did this to scale, wouldn't 66 probably be about here where my finger is, but I didn't have enough room, right? Where you've got a noticeable gap and then you've got a piece of data sticking out like a sore thumb. We have a name for this unusual guy here. And the name that we use is outlier. So if you have a histogram and all the data is like over here, but like way over there on its lonesome is, a single one or two numbers, right? One or two people, then they are called outliers. So you might hear statisticians saying, well, I've collected the data, but I had a couple of outliers. And what they're talking about is like me, right? A 66-year-old isn't a typical person for the rest of the class, right? Yes, Cody.
So whatever is not connected to the histogram is an outlier?
I wish it was as easy as that. No, I wish it was as easy as that. Let me show you the problem. I'm not going to draw rectangles. Can we pretend that's a rectangle, right? You've got a noticeable gap, and then there's me. That is definitely an outlier. You have the same data, and then one little gap, and then it's me. That is not an outlier. An outlier has to be a significant amount of gap, not just one little gap, right? Not just one little space, like there's no 23s and I'm a 24, right? That's not an outlier. Can you see that between this, which is not an outlier, and this, which is an outlier, below dotted line here, would you agree that there is a kind of sliding scale of how far do you move this before it becomes an outlier, right? Okay, which means you do have to sometimes make a judgment call. Right now, you have to make a judgment call. Statisticians hate having to say, I think it is, and you think it isn't, and then we argue about it. So later on, we'll show you that there's a numerical test that you can use on some data. And you do this numerical test and it will say, yep, you're an outlier, or nope, you're not. But let's give you the problem. Right, here is my data, right? And over here is my outlier. Would you agree that's an outlier? Okay. If it was here, is it still an outlier? Yeah, most of you still agree, right? I don't think I've got any dissent. How about here? Still good? How about here? Still good? Nobody disagreeing yet? How about here? Right, I've got at least one disagree, right? I've got one that ain't an outlier. So would you agree that somewhere between here and here, there's a little gray area? And Sydney looks at it and she thinks, yeah, that's still okay, or that's still an outlier. But someone else says, no, that gap's too big, it's an outlier, right? For the time being, we're just going to live with that, right? So that when you describe a data, if you think it's an outlier and then WebAssign says it's not, can't you just switch the answer to it's not an outlier? So you get 5 guesses, so it's not going to kill you, right? But you might want to argue with them and say, I don't think you're right. I'm still sticking to my guns. And in some sense, that would be totally fine. until we show you the test. And then once we show you the test, we all agree on it. So that is what an outlier looks like. So unimodal, bimodal, multimodal. We've talked about uniform, and we've talked about outliers. Okay. There are some other things that we are now going to talk to you about. And here we go. I'm going to use the circle version because it's easier to draw and quicker to draw. Can you imagine data that look like this? Data that looks like this. And the last one is data that looks like this. Now, first, they're all unimodal. Agree? They're all one hill. All unimodal. And I'm not talking about outliers now. But these three are distinct shapes. They are so common, right? When you collect data, these shapes happen so often that it's worth giving them a name. This one in the middle is called symmetric. Does that make sense for a name? Isn't it kind of balanced? The left and right of the hills about the same. It's symmetric. That's the name we give to a unimodal that is balanced, right? It's symmetric about essentially the center of the hill. Now, do you notice that this one goes up and then it kind of, I don't know if I have to make this even more obvious, right? You see how it tails off to the right? This is called right skewed. In some textbooks, it's called right-tailed, but right skewed. You'll also find, I wish I was in charge of statistics, you'll also find it called skewed to the right. I guess I should put in the right-tailed as well as that then.
That's
It's just three names.
That's how it was on the homework, skewed to the right.
Yeah, so skewed to the right. Oh, well, okay. So that's the one that this textbook uses, right? Skewed to the right. That's fine. Right skewed, right-tailed. So if you were talking to someone in, you know, it's a statistical way, right? You're talking about your data, and you could use any one of those three terms, and the other person would probably know what you're talking about, right? So if I went and said to you right now, oh, I collected some data about the heights of some children, and the data was skewed to the right, and it was unimodal. You're getting an idea of what the data kind of looks like just by those sentences. It's skewed to the right, and it's unimodal. And if I went and said, oh God, and yeah, there was a 6-foot outlier as well. Wouldn't you say, God, there's a kid that's 6 foot. He's miles away from all the other kids' heights. You see that word outlier gives you an idea of how to use words to describe something visual, because that's what I'm doing here, aren't I? I'm using words to try and convey a picture, right? So that guy skewed to the right, because that's what the homework wants. That's called symmetric. Now, in this case here, do you see that this fella over this way, the data, I don't know if I should have made it bigger. I'm trying to make it a little bit bigger, right? It goes like that. Isn't this left-tailed? Left skewed, but we're going to call it skewed to the left.
Can a bimodal be skewed?
No.
No.
You might argue that it's skewed, but we don't call it skewed. You might just say it's tails off to the right rather than say skewed. What I'm talking about right now are only for unimodal. So most of the descriptions I'm actually doing from here and from here onwards are going to be about unimodal shapes for the most part, right? Mostly because when you actually collect data, almost all the time, the data is pretty much unimodal, right? That's, you know, sometimes you get random data that has no shape to it at all, which is kind of boring if it does have no shape, because you can't really get anything useful out of it. And it's helpful if it does have a shape, isn't it? It's got a pattern to it. Now, we even have a name for this piece of the shape. Any ideas before I tell you what we call this piece of the shape?
The tail.
It is. It's called the tail. So that's the tail. When it's skewed left or skewed right, we normally just call the tail the long one, right? When it's symmetric, you could really say it's got two tails. Would you agree that each tail is just as big as the other? Right, so we're looking good. Now, you can have a shape that is skewed left, skewed right, and symmetric. And at the same time, it's allowed to have an outlier. It's okay to mix and match them. So I wish I hadn't drawn all this right in here. But can you imagine that this data kind of finished here and there's a little outlier on his own sum? Do you see that? I would still describe this as unimodal, skewed to the right with one outlier. And you can have something that's symmetric and it just has an oddity, right? It's got one outlier, right? I would still say unimodal, symmetric, and one big outlier. The outliers don't need to be big. Can outliers also be very small numbers? So wouldn't that guy over there be an outlier? And wouldn't there a guy over here be another outlier, right? So you could have an outlier at both extremes. But this shape here would be unimodal, skewed to the left with one very small outlier. Cool. Now, I'm going to write down a description of a histogram in English. And this particular one is skewed to the left. It's unimodal. And one large, I'm using a big outlier. In your mind's eye, can you kind of see what that data would look like? Right, it's unimodal, it's skewed to the left, and it's got one big outlier. So I'm now going to try and draw what that picture of that data would look like. Since it is skewed to the left, wouldn't it look something like that? Unimodal, yep, one hill. And one big outlier, wouldn't that make the outlier somewhere over here? Is that kind of what you were seeing in your mind's eye when you were trying to picture this data? So that's the vocabulary, right? The words I'm giving you here are ways to allow you to describe a visual set of data, right? All these numbers made into a histogram. What does that histogram look like? And there would be a good description of it. We're looking good? Now, the next thing I'm going to tell you is not normal for mathematics, but it is very normal for statistics. Nothing in statistics, because it's real life data, is perfectly smooth or perfectly anything. So you won't get a perfectly symmetrical set of data, but as long as it's pretty close, you'll still call it symmetric, right? And you won't get a perfectly skewed left or a perfectly skewed right either, right? You just have to be a bit generous, flexible, whatever word you want to use, when you describe some data, okay? So let me show you some data and we'll see if we can use some of the vocabulary that we've learned today to describe this data. Now, I wish they'd stuck the word roughly in front of all three of those descriptions, but pretend it's there. Is this data roughly skewed left, skewed right, or symmetric? And you have to be really flexible and generous.
Skewed to the right.
I agree. What made you go that way as well, Cody? What was your kind of...
Because it dramatically tapers from 2 to 10 with a big outlier, and it's just an even slope down.
Is that what you're saying, everyone? That's what I'm saying. You see it kind of I know there's a gap there, but kind of fill in the gaps and sometimes imagine things being a bit bigger than they are. Because in real data, aren't you going to get just little idiosyncrasies all over the place? So the way I see this is, can you imagine I'm drawing a line, a curve, up and down? Do you see there's more curvy that way, skewed to the right?
Can there be outliers on the left side of the graph? Yeah.
There could be, but I'm going to say that that guy there is not an outlier. And the reason I'm saying it's not an outlier, would you agree that's not a very significant gap?
Correct.
Now, we might argue about that one, right? Would you agree that that's maybe more of a judgment call on this final one here? My gut feeling is that it's not an outlier. That's what I would argue. I'm not saying I'm right, because I bet you I might talk to another statistician and he would say it's an outlier. It certainly has a noticeable gap. Would you agree? I guess the question is it a big enough gap to be important, right? Nobody, I think, would say this was an outlier. Would you agree one rectangle gap's not a lot? Right, you're going to get that. But right, 3 or 4, we're getting there. Now, if I picked that blue guy and moved him maybe 1 or 2 to the right, so he's where my mouse is, I would be definitely outliering, right? I'd say that's an outlier. I might even agree with you if it was an outlier around about 14, right? If I just moved it 1 more. But I think that particular one is on the boundary. So when you're doing your homework, if it says, is there an outlier, and you say yes, and they say no, that's what's happening. Or if you say no and it ends up being yes, we're in that gray area and one person sees it differently from the other. So here's our question. Is it an outlier?
Yeah, it says it is.
It says it
Yes,
is.
mine's very similar, and it also says that that is an outlier.
So do you know what that means? That I would be disagreeing with it. Agreed? Does it make me right? No. Does it make them wrong? No. Does it make them right or me wrong or whatever? No. Would you get what I'm getting at? There's an argument going on here, right? I definitely would not pick 0, but they're saying it's an outlier, right? And then they talk about why is it an outlier? Well, would you agree that the main reason for an outlier is something to do with there's a noticeable gap, and that's what I would be looking at. Okay. Here's your choices. Oh, they gave you a new name. I should have put that in on my list. I'll do it now. Here is your histogram of data. This is the number of hours slept by 122 college students. So they were asked last night, how many hours did you sleep? And this is the answers that we got. And be very generous. Highly skewed left, highly skewed right, or approximately symmetric. Bell-shaped is another name for symmetric. Because you know the little symmetric, doesn't it look like a big bell? I guess that's why it's called bell-shaped. What are you going for?
Symmetric.
I'd go in symmetric. The fact that they stuck the word highly in front of the skewed, didn't that kind of push you over the edge? Right? Are there any outliers? I don't think anybody's going to argue, including me, with this one. Would you agree? No. Right? I mean, there isn't even a candidate. Would you agree there's no gap? How can you be an outlier if there's nothing, right? They're all together. So at least I won't disagree with them this time. And then you can go in and explain what you got. Now I'm going to look at this data and just answer some of my own questions, even if it's not theirs. First thing that strikes me is that the spread in that data is enormous. One of those students, at least one, it might be 2, I think that rectangle is probably 2. 2 students only slept for 2 hours. And they were partying, right, or working night shift or something. And a little bit more, it's hard to judge, that's probably 3, maybe 4, did 11. So if I was looking at that, I'd say, wow, that's a lot of variation, right? Normal, that's the wrong word. Typical, that's a better word. Typical people sleep, what, 7, 8 hours, 6, 7, 8 hours, maybe 9. So if I did it with you lot, which I'm not because we don't have time, wouldn't you expect a much tighter set of data, right? Where most people are within a small range. So the first thing I noticed is how spread out the data is. If I was a gambling person, would you agree round about 6 or 7 hours is the typical number of hours that a student would sleep? With an extreme of 2 and another extreme of 11. I don't think I can see anything else that strikes me as particularly interesting about that data, but that's what we've got. So far, so good. Now, I'm going to show you the next type of diagram, which is also a histogram, but it's a slightly different version of a histogram. And then we'll show you how salt would do it. So, they collected data. I better zoom over to the white screen. Forgot where I was. Right. They collected data on the blood pressure. I think it's a diastolic blood pressure and the frequency. So a lot of data is collected, medical data is collected about people, and it's used by a lot of medical people for all sorts of reasons. So in the range 45 to 55, there was 8 people. And then 55 to 65, there was 77 people. And then the next one is 65 to 75. It'll take me a while to do this, sorry about that. 263 people. And then from 75 to 85, there's 251. And then keep going, I have 85 to 95 is 76. Almost done. Then I go 95 to 105, which is 22. And lastly, there is 105 to 115, and there was 3 people. And this is
I was
yes.
right skewed.
Oh, you tell me just by looking at the data.
Yeah.
I haven't a clue. You could be right. I don't know yet.
No. Think
You
actually it might be more left skewed.
Or it might be symmetric. We'll find out. I'm not saying you're wrong. I just don't know. It's hard for me to look at just numbers and picture them visually because you have to turn it sideways and imagine heights. And I'm not always very good at that, although I am a visual learner. Let's tell you first what's going on here. This is a grouped frequency table. And 2, 4. This should be, according to them, this adds up to 700. So it's a pretty decent size sample, right? So whatever it is, maybe the doctor, your doctor, just collects your blood pressure. You know, when you go in and get your doctor's visit, they take your blood pressure, at least they do in my case, and they've got it recorded, and he just goes and looks at his records or her records, and she's got 300 patients or 700, and this is the data. And so why is it grouped? Well, a couple of features you got to watch about group frequency tables. Typically, each group must be the same size. So you can't have 10 numbers in this group, 50 in that one, 22 in that one, and 17 in that, right? I guess you could if you wanted to, but we don't. Can you see why it's a good idea to be consistent, right? So each group should be the same size. Would you agree each of these is about 10 units? Secondly, why don't they just count all the 45s, all the 46s, and all the 47s? Well, if you did that, what your histogram would look like would be blood pressure along here. Do you know that you'd get maybe lots of gaps and not many people at any particular place? Wouldn't it look like that. It would be really long, right? It would go from 45 to 115, right? That's about 90 numbers, right? And even if you've got a lot of data, you don't get to see any real shape. You know, if I continue that, like 2 pens, can you imagine? Just a dot, 2 dots, 4 dots, you know, all the way along. So what you do very often is you group the data, and it allows you to combine a whole group of numbers. Now, has anybody noticed that there's a little problem here? That this group is 45 to 55 and this group is 55 to 60, right? If you notice that they both are 55. So you might think, well, somebody's going to have 55, right? Somebody's blood pressure could easily be 55. And so how do you handle that? Well, 55 to 65, that group there, means 55 up to, but not including 65. So if someone was 55, they get counted in this group here, right? If their blood pressure was 55. If their blood pressure was 54.9, wouldn't they be in this group? So do you see that that's actually not a contradiction? Once you realize that that is that, can you see that they're not going to write that big sentence in every single one of these? Because that's just overkill, isn't it? So we just assume that you know it.
Oh, I was going to wonder, I'm guessing is with the way that the little gap between, is it sometimes used to try to create make the graph look manipulate the appearance of the graph by choosing the just right
Intervals.
Yeah.
Yeah. You could up to a point, but you couldn't really distort the data too much. I mean, if you made first rule is you must make the intervals all the same size. If you make them different sizes, sure, you could cheat as much as you want there, couldn't you? Right, you could have one huge group, so the tall rectangle in that point, but no one's allowed to do that, so that's not going to be a main issue. So how do you draw one of these guys, right? Well, it's going to be a histogram, so you go like this, and obviously blood pressure and frequency, that's not going to change. And I might as well start at 45, and then you go 55, then you go 65, then you go 70, 85, 95, I guess I better keep going here, 105, and then finally 115. Obviously you would do it in square paper and you do it neatly. Now the first group is 8, so what do I need? I need 260, so okay, 1, 2, 3, 4, that's 100, 200, there's 300, and so I'm going up in 25s if you're wondering. I'll skip the others because it takes too long. Right, so 45 to 55 is 8, which is about there. Then 55 to 65 is about 77, so it's just a tiny bit above that one. And then the next one is 263. So there's 250. So 263 would be probably about here. And 251 is about here. 76 is about here. 22 is about here. And lastly, 3 is probably about here. Okay, that's what my group frequency table, that's what my histogram looks like. Now that I can see it, I'm going to go for symmetric. I think it's symmetric and very roughly symmetric. I don't think there's enough difference on this side compared to that side to be a skewed right, but that's my opinion. Right, it's got a little bit more on this side than that, but I don't think it's enough to be significant. And that's how you would do it by hand. So don't you want to see how you do it using software, so you don't have to spend anywhere near as much time? So I'm going to try and show you what that looks like. Yeah. So here is the data that I just used. Here are the 4 charts. Right. Now, based on what I've just drawn, would you agree it was that one? If you remember the picture I just drew, it looks like this one. Now I'm going to hit salt. There we go. And I'm going to go to charts and hit histogram, I hope. Oops, I will hit bar chart. Oh, they're calling it a bar chart. Oh, come on. Oh, they're driving me crazy here. Okay, can I go back? No, I can't. Damn it in space. Before I hit that bar chart, fella, which is this one here, right? That guy there. Didn't the pictures have histograms? So this is WebAssign just being a pain in the butt. So there, can you see it? So I'm not sure why it didn't do or didn't give me the choice. So I'm going to see if I can make it happen again. Okay, here is the data. I've selected it. Yep, I'm going to go to charts. I'm going to try histogram. And it's not allowing me. Okay. So I guess the moral of that story is that button was useless for this question. Although you could have done, couldn't you have basically got the shape by using the bar chart? And the only difference is make the little gaps disappear, right? And you would get the shape. So I was hoping that there was more to it than that. And then here are some questions. Provide a summary of that histogram. And say they're even calling it a histogram. And in my case now, it ends up being that shape, right? And there's some sentences, and you pick which one it is. And why you can't use a stem and leaf. They haven't mentioned the stem and leaf until we get to question 8. So let me show you what a stem and leaf looks like. That way, when they say, why can't you use a stem and leaf, the question will make more sense. I'll imagine that you want to create a different kind of picture. Instead of a histogram, right, as we've done, you want to create another picture, and this particular picture is called a stem and leaf. And I'm going to, because they're quite time consuming, I'm going to create some false data and then use it to make one of these happen. So we collected some data on some ages of people. And on forever. I'll put a 10 in here and a 9, right? So imagine you've got like 100 people's ages, right? So you went to, I don't know, some club and you got the ages, everybody who was a member of this club. And these are the kind of ages, and they're all jumbled up, right? So the way a stem and leaf works is you start off with a vertical column called the stem. And you look at your numbers from the smallest to the biggest. Can we pretend that I had a 91-year-old in my data, right? Just to give you an idea. And you put down 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So on the top, the smallest, and on the bottom, the biggest. And now you go like this. A 9-year-old goes there. A 10-year-old, a 12-year-old, a 13-year-old, a 15-year-old, a 27-year-old, a 63-year-old, a 57-year-old, a 33-year-old, and a 91-year-old. Do you see how quick it was for me to take all these numbers and make it into this chart? Do you see how I did it? Right. Now, when you do a stem and leaf, you have to tell people a key. And what you do is you just randomly pick one of your data points and you go 2/7, that guy, and you tell them what it means. It means that they're 27 years old, right? Because couldn't you do this data with 1.5 and 2.7 and 3.7, right? It could be decimals, in which case 2/7 would mean 2.7, right? So the reason the key is there is so people can take this, because they won't get to see this data, and they get that. So let's just pretend that was all my data, right? So I collected all my data, and that's my finished stem and leaf. Now, if you take a stem and leaf, as we have here, and you do this to it, do you see a histogram? Not a very nice histogram, but do you get the feeling of a histogram? Can you see its shape, roughly? Does that make sense? That you can actually get an idea very quickly what the basic shape of this is. So let's try this out. Unimodal or bimodal?
Bye.
Yeah, I'd probably say that that's definitely a hill, and that's probably separated enough. You could argue maybe it's not, but I'm going to say it is. Do you think this one has an outlier?
I think so.
Yeah, and some of you don't, but we've came across that problem before. Trust me, eventually I'm going to show you a calculation where we tell you how to tell. But right now you're eyeballing it, and I'm going to go with it. I think it is. But if some of you think it isn't, I can understand why you think so, right? I'm not saying you're wrong. I'm just saying it's an opinion, right? So there is how you create a stem and leaf, right? Now, what's its advantage? Well, can't the data be all jumbled up and it doesn't matter? Can't you create your stem and leaf pretty quickly, even when it is jumbled up, right? I didn't need the data to be in numerical order, right? And what's not so good about it? Would you agree that it's not as clean or pretty? You know, although I've done that, that's not really a very nice diagram, right? It's a bit rough and ready. So that's probably one of its biggest drawbacks. The next drawback I deliberately made not happen here. But if you just have your data jumbled up, couldn't you quite easily get, for instance, this set of data might have came up like that? Couldn't that have been the order that I read them? But when you make a stem and leaf, you have to put them in order from smallest to biggest. So doesn't that mean you might actually have to do 2 stem and leaves? The first time round just to get the numbers, and then the second time round to put them in order. So that's a drawback, because you have to do it twice. So when people do stem and leaves, they are always in order, right? You notice it's 7, 8, 8, 9, 9. It's not 8, 7, 9, 8, 9, because that's just, when I did the numbers, that just happened to be the order that I found them in, right? Are we
I don't
good?
understand the key.
Oh, the key, 2/7 means 27. Okay.
Okay, so for the 09, what is that? Just 9 years
Oh,
old?
yeah. 0/9. I guess it means 09, but really that just means 9.
Oh, okay, so the 1, 0, 1, 2, so that's 10, 12, 13, 15.
Yeah, you got it. And
Okay.
63, 65, 67, 68 makes sense now.
91. Okay, yeah. perfect.
91, right? And for people who are not used to them, I guess that's another drawback. Aren't stem and leaf, you've got to understand what you're looking at to understand what the data is. You have to realize that there, for instance, in this case means 68. So back
you.
to that question where we did this one. Remember the group frequency table one? This one here? And the question says, why can't we do a stem and leaf using these numbers? So why can't I make one of these diagrams using this table of values, this frequency table? Any suggestions?
Don't have data in that form, maybe?
Yeah. See this 8, all I know for sure is that it's some number between 45 and 55. I don't know if it's 46, 47, 47, 52 and 53, right? I don't know what those numbers are. And to do a stem and leaf, don't you need to know every single number individually? You can't do it if it's all the numbers from this range, but I can't tell you which particular number it is, because I need to know which particular number it is, right? Because wouldn't 45 go here and wouldn't 55 go here, right? And I don't know from this that detail, because one of the drawbacks of grouping the data is, don't you lose a little bit of information there? All I know is that there were 77 people in that blood range. I don't know whether there was a lot more 50s and not many 60s or whatever the combination is. I just know in total there was 77 in this group. And that's a little bit of lost information.
Well, the information going off the stem, that's the leaf.
Oh, I didn't mention that. This guy here is an example of the leaf. Yes, that's exactly what it is. So, whoops.
Is all the data a leaf or just the outlier?
No, all of them.
Okay.
So that 4 is a leaf and that 3 is a leaf. And these blue ones are stems. So that's a stem, that's a stem. The whole thing is called a stem, but any one of them is part of that. And all the red numbers, right? They're all the leaves. So that 8 is a leaf and that 8 there is a leaf and that 3 is a leaf as well.
Perfect. And in order to do a stem and leaf, you have to have the exact
Yeah,
information.
you have to have individual numbers, right? You have to have the exact number for all of them. You can't do it if they group the data.
Okay.
And I think that's a very natural point for us to finish.